Here we are, back again, learning us some pure mathematics over the internet. So, we covered what the basic types of statements that we're going to be encountering, no matter what sort of argument we're going to be making, mathematical or otherwise. And those are the words if then, and, or, and not. We will definitely be encountering those words, and we will definitely be talking about whether or not things are true or false, regardless of the argument that we're talking about. So this is not just a component of mathematics that we're learning right now, but we're actually learning a little bit of philosophy. And now that we've gotten all of the basic building blocks out of the way, those small statements that every other argument is made out of, we can start to build some of the larger, more complicated statements that we love using but are less basic. They're composed out of the things that we've talked about before. Chief among those, the most important thing to discuss, is the idea of logical equivalence. Because logical equivalence, in many ways, is like the equal sign of the world of logic. We don't really have an actual equal sign here, because it doesn't really make sense to say that one statement equals another. The only time that would really be meaningful is if the statements are exactly the same. And, well, that's not so exciting. It's pretty clear that two statements that are exactly the same are the same. That's kind of what you mean. But you can have two statements that, even though they use different words, are only ever true or false simultaneously. No matter what words you use to construct them, logically, they have the same content because they're only ever true or false in precisely the same situations. When two statements share this quality, regardless of the words used to compose them, we say that these two statements are logically equivalent. And just like how when you had two different representations of a function or a number, and knowing that they were equal allowed you to substitute one in for the other whenever you felt like it, knowing that two statements are logically equivalent means that you are able to substitute one for the other in any situation that you desire. So this property of logical equivalence is incredibly important. It allows us to use the powers of substitution that we were very, very happy and familiar with in algebra if we spent a long time doing that in school. So now that we know a little bit about why we would care about logical equivalence, we get our substitution power even here in logic. Let's talk about what it actually means for two statements to be logically equivalent in terms of the language that I've already given you. I gave you the heuristic explanation that those two statements would have to be false and true at the same time. But that can actually be said incredibly precisely using the and if-then statement that we defined last time. Specifically, I'm going to say that two statements P and Q are logically equivalent if the following statement, P implies Q and Q implies P, is true. If this statement right here is true, then I will say that P and Q are logically equivalent, and in order to write that out, I will simply write this. So these two different symbolic expressions involving Q and P are the same. Whenever I write this, I mean that, and vice versa. Once again, we are mathematicians. We're quite lazy, so in any time we're given the opportunity to shorten what we're saying, we will do so. All right, so now that we can see this logical equivalence statement, what it actually boils down to, we can see that in order to prove, guess I'm going through puberty a second time. In order to prove a logical equivalence, in order to prove a statement like this, I'm going to need to prove two implications. I'm going to need to prove this implication, P implies Q, and I'm going to need to prove this implication, Q implies P, because I'm proving an and statement. And in order for an and statement to be true, like we talked about last time, both of the components, this and this, have to be true. So there's a whole lot of work that goes into proving an equivalence statement when you compare it to proving an if-then statement, because it is literally twice the amount of work. So now that we've seen that, I'm going to give you an example of a logical equivalence All right, so now that we know about equivalence and we know how these things are, or how these types of statements need to be demonstrated, we need to do two if-then statements. Let's get a simple example. So we've all likely solved lots of equations, and if there's one equation that basically all of us know how to solve, it's that guy right there. Ax is equal to b. He's got a super easy solution criteria. Basically, I can always solve him as long as a is not 0. So let's go over real quickly why we all know that, because we do all mostly know that, and it'll be a really good example here to show off the procedure for a logical equivalence proof. So like I said before, we're always going to be proving two if-then statements. One where we assume the first statement and then prove the second statement, and then vice versa, where we assume the second statement and then prove the first statement. So let's start off with that first one here. So our proof is going to begin as though I was just doing an implication going that way. So first, assume our first hypothesis, which is that a is not equal to 0. So I want to show that now that I've assumed that a is not equal to 0, I want to show this statement is true, that a times x is equal to b has a solution. And it's actually pretty easy because we've all probably solved this before. As soon as I know that a is not 0, then I can make the number b over a, where we're just assuming that we've given ourselves a b here and we know what it is. B over a is a number that is definitely defined. Why? Because I always know how to divide any two numbers as long as the second number, the one I'm dividing by, isn't 0, which is exactly what I assumed. So I make use of that assumption immediately by saying that I can define this new number, this fraction, and as I'm sure you expect, this fraction is in fact the solution that I seek, which we can verify very quickly here if you don't believe me, because a times b over a causes the a's to cancel out, giving us just b, which is exactly the equation that we set out to solve. Therefore, this number, b over a, since it clearly exists, there it is, and it solves our equation, the second statement, that this equation has a solution, must be true. All right, so that was super easy. I'm picking these examples so they're close enough to the ground so that we can all follow them no matter where we are. But so that was our first direction. We've proven that this hypothesis implies this conclusion. Now let's go back the other way. So we're going to start by assuming that this equation has a solution, and I'm going to divine from that a can't be 0. So how are we going to do that? I'm actually going to make use of something that we haven't talked about yet, I don't think. No, wait. We did talk about this. We did potentially. Oh gosh, I'm going to have to go back and look at that first video. But if I didn't go over the idea of a proof by contradiction, then this is the first place that it's going to be showing up in this series. A proof by contradiction is an indirect way of proving an if-then statement, an implication. Instead of just assuming the hypothesis, which is the procedure that I gave you last time, I'm going to assume the hypothesis and I'm going to assume the opposite of my conclusion, which is basically saying I'm going to assume that I'm wrong. And there's a reason why I'm doing it. A statement, like the ones we've been using, P and Q, a statement is defined by the fact that it is only ever true or false, but not both or neither. So, if I can, through an argument, pull out that some statement is both true and false, I will have broken logic, and that means that whatever assumptions that I started out with in my argument, they are incompatible with one another. I cannot assume all of them, or else I break the world. So if one of them is true, then the other one has to be false. They can't be true simultaneously. So that is what I'm going to do here to prove the second one. I'm going to assume my hypothesis here that this is true, and I'm going to assume the opposite of this. I'm going to assume that a is equal to 0. I'm going to show that that breaks math, and because it breaks math, I can't have both of them. I can't assume this and then assume the opposite of this. If I assume this, the only logical choice that I can make to move forward without breaking the system of the universe is to assume that a is not equal to 0. So that's an alternative way to prove an if-then statement. So now that I've introduced that as a concept, let's move on through this. So like I said, I'm proving this in the if-then statement this way towards this way. And I'm going to start out by assuming that this equation, a times x is equal to b, has a solution. In my second step, I'm going to assume that I'm wrong and say that, suppose further, that a is in fact equal to 0. All right, so we've set up the proof by contradiction introduction. I have assumed my hypothesis, and I have assumed the opposite of my conclusion. Now, the intervening steps will always look like me trying to break the universe somehow with these two assumptions that I found. As soon as I've broken the universe, I can immediately throw one of my assumptions away, say its opposite must be true, and that generally gives me the proof that I'm looking for. So, how is it that knowing that this equation, a times x, is equal to b, which is definitely not equal to 0, how do I know that this thing, actually having a solution, causes the universe to break if a is equal to 0? Well, if a is equal to 0, then 0 is definitely equal to 0 times x, because anything times 0 is always 0. And we know that a is equal to 0. That was our contrary assumption. So I can just substitute a in for 0 here, and I get that 0 is equal to a times x. Well, that's sort of a problem, because I know that a times x, by my equation having a solution, x being that solution, I know that a times x is equal to b. But one of the things that I assumed about b was that b is not equal to 0. And here's our contradiction, because I've just written 0 equals, a whole lot of other stuff that we can ignore, not equals 0. You can't have 0 not equal itself. That doesn't make sense. That is exactly what I was saying we were looking for. We have broken the universe. I found a statement and its opposite. 0 equals 0 is the statement that's unwritten here, because I don't have to write it down, but 0 equals 0 is always true. And 0 not equals 0, well, that is an opposite of a true statement, but this argument is also claiming that it is true. So this statement is both true and false, that 0 is not equal to 0, and that's a problem. We can't have those. Remember, statements can only be true or false, and so since I've now constructed one that is both, that is our revelation. That reveals to us that at some point during my argument, I asked you to assume something ridiculous. So let's go back to our list of assumptions, and the first one that I make that isn't my hypothesis is the one I have to throw out. All right. So my hypothesis was me assuming that this equation actually had a solution. Can't throw that out because I need that. What's the only other assumption that I made, though? It was supposing further that a is equal to 0. Well, now I know that if I assume my hypothesis, and then I assume that a is equal to 0, I literally break the universe. So, I have only one choice going forward with my life. A must not equal 0. Because the universe can't break. We live in a universe where logic works, and cause and effect continue to occur, despite our arguments. So, it must be that a is not equal to 0 here. So that is and that was fairly long-winded for the example that I chose, but I really wanted to go over everything here in detail. And that's always what the procedure for proving a logical equivalence is going to be. I'm always going to be doing two if-then statements, going in opposite directions. The conclusion of the first is going to be the hypothesis of the second, and vice versa. When I have a statement like this, now that I've proven, then anytime I see an equation like this that has a solution, or I see a number like this that's not equal to 0, I could sub in either one of these statements for the other. They're totally equivalent. And in fact, this is the procedure, it's a very important procedure, that's used in linear algebra, which is where I was trying to sort of take a baby example from. This isn't exactly what you would see in linear algebra, but in linear algebra we have some very, very important theorems on the existence of solutions to linear systems of equations. And what it essentially comes down to, I don't have this written in matrix vector form, if you know what that is, but if A was a matrix and B and X were vectors, then this would all still totally be this would all still totally be a reasonable statement to go off and prove. The only thing I would have to change this to is instead of a not equal to 0, it would be the determinant of a is not equal to 0. And now we have some of the most important theorems in linear algebra, that the solution to a linear system of equation is always solvable in general if the matrix, the linear transformation involved, is invertible or has determinant 0, because those are equivalent statements. And so as you go out into some other subject like differential equations or linear algebra, or heck, just number theory or combinatorics, you can go out and encounter these many interesting, useful statements that you want to find out, like a has determinant 0 or a is equal to 0, an equation has a solution, and build yourself a huge number of bridges between them that allow you to calculate things that you previously thought were impossible. So that is, I won't be able to show you the that exact thing going on for a while now, because I've got quite a bit of set theory to teach you before we really see all of the cascades that are going to start occurring from all the equivalence statements that we've proven. But we will at some point be logically substituting things left and right, because we have that kind of power now, and it's pretty cool. So now that we've got that example proof that actually involves a little bit of writing and steps out of the way, something that's actually got a little bit of math that you can sink your teeth into, let me talk to you about the sort of big theoretical equivalences that I want to discuss in this video. And these proofs, or rather the proofs of these equivalences, are not quite as meaty. There's not really a whole lot to sink your teeth into. I'm just going to write out some truth tables and reason as to what they are. And once we see at the end that the truth tables of the two statements are equivalent, we must be forced to conclude that they are equivalent, because all logical equivalence sees is your truth value, whether you're true or false, and since they will be true and false in the same cases, they must be equivalent by our definition. So I've already got one of them written down on this piece of paper. Also, I've switched from paper, switched from a whiteboard to paper due to some time and space constraints here, but it is of no consequence, makes no difference. So let's get on with actually calculating this. So yeah, the implication statement, which is one of the things that I'm drawing equivalence between, has already been written down, and so is its truth table. The implication statement is almost always true. The only time he's not true is when the hypothesis is true and the conclusion is false. So the person who's saying if then is wrong. Okay. So and I'm going to try to show you that it is equivalent to this sort of statement here, where I reversed the order of P and Q and stuck knots in front of both of them. It's what's known as the contrapositive statement, and it turns out that it's equivalent. And how I'm going to show you that to you is I'm just going to fill in this truth table, just using the rules that we know from our definitions of knots and implications and such. And then we're going to see that they're the same. So to do that, let's remember that, and it's not easy, it's not hard to forget because I've literally got it written up here, but for the implication, for the truth table of an implication, up there at the top, it's only going to be wrong once. It's only going to be wrong in that spot. When the conclusion is false, the conclusion is false and the hypothesis is true. So over here, the hypothesis is not Q. Not Q is true when Q is false. So we're going to be in this column when this statement over here is going to be false. So not Q has to be false, or Q, has to be false, because that makes not Q true. So that's the first of the criteria that we need to make an if-then statement false. The next thing I need is its conclusion. The conclusion here is not P. I need that to be false. So not P is false. Not P is false when P is true. So it's got to be in this row, this column, this row. That's our only failure, because an if-then statement can only fail once. And so that means the rest of these columns have to all be truth, which is exactly what I have written up there. No work, no teeth sinking into. There's really nothing to be done here. It's fairly clear just by studying truth tables that an implication is always equivalent to its contrapositive. So there, massive logic theorem proved with tables. Bam. Exciting. Okay, so this is actually going to give us another equivalence for free, but I'm going to have to clear my paper first, so let me do that briefly. All right, so the equivalence that we get for free just from knowing that an implication is equivalent to its contrapositive is that the converse and the inverse of an implication are also equivalent. So what the converse and the inverse are obviously needs to be mentioned. This here, if I have a statement P implies Q, this is the converse. Q implies P, where I've just swapped the order of my two arguments. This thing over here, not P implies not Q, that's the inverse of P implies Q. I've just taken both the arguments and inverted them. I've hit them with the not. So I know that these things are equivalent because using the equivalence that we just got, I can take the inverse here, and I know because he's equivalent to his contrapositive that I can invert both elements and swap their orders to get an equivalent implication. But the not of a not is just the original thing, which means that this is equal to the Q. Q implies P without those double knots there. And that's exactly what I said I was going to set out, the extra equivalence that I said I was going to get for free. So that's not all that exciting. It's not a whole lot of work to get that, but it's nice when our tools already start giving us things for free. We're hoping that happens a whole lot more often. And we've already got some general statements that we know are always equivalent. We can always substitute a contrapositive for an implication, and we can always substitute the converse for the inverse, or vice versa, of some implication. All right, so that wasn't terribly much work, so let's continue using this sheet of paper to get something done. And the thing that I'd like to get done is to prove 1/2 of De Moivre's theorem, or De Moivre's laws. De Morgan's laws. Yeah, not De Moivre. Ugh. Not wrong person. De Morgan's laws. So De Morgan's laws tell me that when I take the not of an and statement, it's the or of the nots, and vice versa. When I take the not of an or statement, it's the and of the nots. So I'm going to show that for one of those cases because the other one is exactly the same. It just uses these truth tables that I showed you for the last equivalence, and as we can see from doing this, it's almost no work at all to go and fill in a truth table. It's one of the easiest ways that you'll ever be able to prove anything ever. So this will not be beyond you if you've watched the previous two. If you've watched the last proof and are watching this proof, you'll be able to go on and switch out the and symbol for an or symbol and the or symbol for an and symbol and pull this off just fine on your own. So, and I encourage you to do so because mathematics is a subject of getting one's hands dirty. So anyway, filling in this table, I'm trying to take the not of an and statement. I'm starting with the top one. And we'll have to remember that an and statement is like the most exclusive sort of statement between the ands and ors. An and statement, he's almost always wrong, because for an and statement to be right, both things have to be true. That's the only case where an and statement is right. So if I didn't have the not here, and that's usually how I like to think about these things, I used to like to do it in sections. If I didn't have the not here, then this would be the only place the statement was true. But since I do have the not there, it's going to do the opposite thing, and it's going to make this false. Now that was the only place where the and statement was going to be true, so everything else has to be true after I put it through the not. Excellent, not a whole lot of work there. And that's generally the strategy to go for with truth tables. If you know that there is a particular value that's only going to occur once and everything else is going to be a particular way, that really cuts down on the amount of work you have to do. All right, so let's do the same thing here for an or statement. I've got this or. It's not P or not Q. And let's once again, get rid of the or the nots. Let's pretend we're just talking about an or statement for a second. An or statement is the least exclusive out of the two, out of and or. An or statement is almost always true. So this statement over here is almost always going to be true. There's only going to be one situation in which he's going to be false. An or statement is only false if both of his components are false, because he's true when any one of his components, just one of them, is true. So both of them have to be false here. So I need not Q and not P. I need both of them to be false. Well, not Q is false when Q is true, and not P is false when P is true. So that guy right there, that's the only place that or statement is going to be false. So everything else is going to be true. And wow, that's looking familiar, ain't it? Ooh, those squeaks are something awful, but this equivalence isn't so bad. And that is, I did and just then, yeah. And that is, indeed, proof of at least part of De Morgan's laws. Not De Morgan. This is part of De Morgan's laws. The other one is just when I swap out the ands and ors here. So let's switch this with an and switch that with an or, and that would be the other one. And that is the one that I am imploring you to do. You will find the use in these logical equivalences quite often. You'll be given many times in mathematics either statements that are similar to the ones that you have, or in some form that is understandable to you but difficult to prove. And you can modify it always by replacing it with an equivalent statement in such a way sometimes that it's easier to prove. So that's really one of the reasons why we go out and use these logical equivalences. The other reason would be for translation purposes. It's quite frequently that you don't say the same thing the same way, every single time you say it. Often you say it in different forms. And so when you re-say something in slightly different language, but it is in fact equivalent, you might want to know that. You might want to be able to rigorously determine whether or not you've just said two equivalent statements. And this is the method by which you go about doing that. You go and see if every single piece of your argument can be made equivalent to the other pieces. And if you can, then you've got two equivalent arguments. Now, this is an introduction to pure maths series, not an introduction to logic series, or even a quest for logic, a logician's quest into mystery. We're not here to just study what statements are equivalent. So I'll only be using this insofar as I need to say two statements are equivalent so I can make my job easier later on. But when I do that, when I just go on and change statements all willy-nilly in the future, and they look just a little bit different than the last time I wrote them down, know that I am changing them to an equivalent form, because if I wasn't, I would be doing bad mathematics, and you should be checking me. You should always be checking to see that the thing that I've written down is equivalent, because if it isn't, then I'm lying to you. I've made a mistake, and you will be able to call me on that because everything will be transparent. All right, so that is the notion of logical equivalence. The only other thing that we've got to discuss now is, well, I've shortcut myself. I originally wanted to do one more meeting to discuss De Morgan's laws, but I think I can actually wrap this up right now. So I've got one of De Morgan's laws on the paper right now. You can swap out the and the or symbols to get the other one. So there's really only one other proof from logic that I could possibly need to show you. So I'll show that to you next time when I go over those fellows, that last little proof, and it will be concerning what happens when you take the not of an implication. So one more equivalence proof there, and then I'm going to introduce to you what are called logical quantifiers, the idea of knowing how many things you're asking for when you're in the midst of an argument. So that's the last little bits since I've moved things up a little bit this time around. And once we're done with that, that's all the logic that we could certainly cram more logic into the series. That's all the logic that I'm going to force you through. We won't be needing any more of it to jump into sets, which are the next stop on our road. We are going to need set theory if we're going to do any advanced mathematics. So that's going to be where we're going to be spending some time after this. So until our next meeting when we wrap up logic, I'll see you then.